Space travel has always captivated our imagination. We dream of reaching distant stars and exploring the cosmos. To achieve these dreams, we need revolutionary propulsion systems. Traditional chemical rockets, while powerful, are limited by their fuel efficiency. We need engines that can travel farther and longer on less fuel. This is where ion thrusters come in. These incredible devices hold the key to unlocking the secrets of our solar system and beyond. Ion thrusters represent a giant leap forward in space exploration, offering unparalleled efficiency and the promise of extended missions to the most distant reaches of space. Ion thrusters are electric propulsion systems that generate thrust by accelerating ions. These engines work by harnessing the power of ionization and electrostatic acceleration. Ionization is the process of adding or removing electrons from an atom or molecule, creating an electrically charged particle called an ion. These ions are then accelerated to extremely high speeds using an electric field. This acceleration produces a force or thrust that propels the spacecraft forward. An ion thruster comprises three main components: the ionization chamber, the grid system, and the neutralizer. Each of these components plays a crucial role in the functioning of the thruster, working together to create the thrust needed for spacecraft propulsion. The ionization chamber is where the magic begins. This chamber is designed to facilitate the ionization process, which is the first step in generating thrust. Propellant, typically xenon gas, is injected into this chamber. Here it interacts with electrons emitted from a device called a cathode. The choice of xenon is due to its high atomic mass and ease of ionization, making it an efficient propellant. This interaction causes the propellant atoms to lose electrons and become positively charged ions. The ionization process is critical as it transforms neutral atoms into ions that can be manipulated by electric fields. Next, the ions encounter the grid system, which consists of two or more grids with thousands of tiny holes. These grids are meticulously designed to ensure the efficient acceleration of ions. A high-voltage electrical potential difference is applied across these grids, creating a powerful electric field that accelerates the ions to tremendous speeds, often exceeding 20 kilometers per second. This acceleration is what ultimately generates the thrust. This expulsion of high-velocity ions generates thrust. The force produced, although small compared to chemical rockets, is continuous and highly efficient, making it ideal for long-duration space missions. Finally, the neutralizer, located outside the thruster, releases electrons into the path of the accelerated ions. This step is essential to prevent the buildup of charge on the spacecraft. This neutralizes the ion beam, preventing the spacecraft from becoming negatively charged and ensuring that the ions can escape into space, maintaining the electrical neutrality of the spacecraft. This entire process allows the ion thruster to provide a steady and efficient thrust, propelling the spacecraft through the vast expanse of space. Unlike traditional chemical rockets that produce short bursts of intense thrust, ion thrusters generate a very small amount of thrust. Imagine the gentle pressure of a sheet of paper resting on your hand. That's about the amount of force an ion thruster produces. However, what ion thrusters lack in power, they more than make up for in efficiency. They can sustain this thrust for months or even years, gradually increasing the spacecraft's velocity over time. This makes them ideal for long-duration missions where fuel efficiency is paramount. Ion thrusters are incredibly fuel efficient because they expel their propellant at incredibly high speeds, maximizing the momentum exchange and requiring far less propellant mass compared to chemical rockets for the same mission. Section 5. Building an ion thruster. Materials matter. Building an ion thruster is a complex undertaking that requires specialized materials capable of withstanding extreme conditions. The ionization chamber, for example, must be resistant to the corrosive effects of the ionized propellant. Therefore, it's often made from ceramics or special alloys. The grid system, subjected to high voltages and temperatures, demands materials with exceptional electrical conductivity and heat resistance. Molybdenum, known for its high melting point and strength, is a common choice for grid construction. These materials are carefully selected not only for their durability, but also for their ability to maintain their properties in the harsh environment of space. Section 6. From design to launch, crafting ion thrusters. The creation of an ion thruster is a meticulous process that involves several stages, from initial design and simulation to rigorous testing. This journey from concept to reality is a testament to human ingenuity and technological prowess. It all begins with sophisticated computer simulations that model the behavior of ions within the thruster. These simulations are crucial as they allow engineers to predict how the thruster will perform in the vacuum of space. Engineers use these simulations to optimize the shape and configuration of the thruster's components for maximum efficiency and performance. Every detail is scrutinized, from the ionization chamber to the magnetic field configuration. Once the design is finalized, the manufacturing process begins. This phase involves translating the digital blueprints into physical components, a task that requires both precision and expertise. Highly skilled technicians fabricate each component with extreme precision, employing techniques like electron beam welding and precision machining. These methods ensure that each part meets the stringent standards required for space travel. The assembly process is equally demanding, requiring a cleanroom environment to prevent contamination that could compromise the thruster's performance. In this sterile setting, technicians meticulously assemble the thruster, ensuring that every component fits perfectly. Before an ion thruster is deemed ready for space, it undergoes a battery of tests that simulate the harsh conditions it will face. These tests are designed to push the thruster to its limits, ensuring it can withstand the rigors of space travel. These tests include vibration testing, thermal cycling, and performance evaluations in vacuum chambers. Each test is critical, as it verifies the thruster's durability and reliability under extreme conditions. Only after passing these rigorous tests is the ion thruster integrated into the spacecraft, ready to embark on its mission to the cosmos. This final step marks the culmination of countless hours of design, testing, and assembly, all aimed at propelling humanity further into the stars. Section 7: Ion Thrusters in Action: Missions to Distant Worlds. Ion thrusters have already played a pivotal role in several groundbreaking space missions. These advanced propulsion systems use electric fields to accelerate ions, creating thrust far more efficiently than traditional chemical rockets. One notable example is NASA's Dawn mission, which explored the asteroid Vesta and the dwarf planet Ceres. Launched in 2007, Dawn's journey provided invaluable data about these ancient celestial bodies. Dawn's ion thrusters allowed it to travel to these distant celestial bodies and orbit them, providing unprecedented insights into the early solar system. The mission's success demonstrated the potential of ion propulsion for deep space exploration. Another remarkable mission is BepiColombo, a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency to study the planet Mercury. Launched in 2018, BepiColombo aims to unravel the mysteries of Mercury's magnetic field and surface composition. BepiColombo relies heavily on ion propulsion to reach Mercury and withstand the sun's intense gravitational pull. The mission's complex trajectory includes multiple flybys of Earth, Venus, and Mercury itself. These missions highlight the capability of ion thrusters to enable long-duration missions and reach destinations that would be impossible with conventional chemical rockets. As we look to the future, ion propulsion will be crucial for ambitious missions to even more distant worlds, potentially paving the way for human exploration of the outer solar system and beyond. Section 8: Limitations and Challenges: A Balancing Act. Despite their advantages, ion thrusters also have limitations that engineers are constantly working to overcome. One primary limitation is their low thrust level, which makes them unsuitable for missions requiring rapid acceleration or maneuvering in strong gravitational fields. Their intricate design and the need for specialized materials also make them relatively expensive to manufacture compared to some other propulsion systems. Moreover, ion thrusters require a substantial amount of power, which can be challenging to generate with solar panels, especially for missions venturing far from the sun. These challenges highlight the ongoing need for research and development to improve the performance, affordability, and power efficiency of ion thrusters. Section 9: The Future of Ion Propulsion: Reaching for the Stars. The future of ion propulsion is bright, with ongoing research and development focused on enhancing their capabilities. Scientists are exploring new propellant options such as krypton and iodine, which could offer higher performance and efficiency. Advances in materials science are leading to more durable and heat-resistant components, enabling ion thrusters to operate at higher power levels for extended periods. Furthermore, innovations in power generation, such as more efficient solar panels or compact nuclear reactors, hold the potential to overcome the power limitations of ion thrusters. With these advancements, ion thrusters are poised to revolutionize space travel, enabling missions to the outer planets, interstellar space, and